Okay, hello everyone. In this video, I'm going to talk a little bit about the concept of work and power in physics, right? And there is a question here in the beginning that says, how much work is done by you when you push against a tree? So let's answer that question later after I do a little bit of an introduction in defining what work is and what power is in physics. Now, if I take an object on a surface and then I make a list of all the forces that are acting on it. So let's just say I have a force acting at an angle this way. Actually, I'll go horizontal first. There's an applied force. Yeah, maybe there is some friction. And you can have your normal force, which in this case is equal to your mg. Okay. And let's say the object moves a certain distance, d, okay, and a certain amount of time. Now, if I want to make, whenever I talk about work in physics, I talk about work to a specific force. I can't just say work in general and stop. I have to say, what's the work done by this force or this force? All right. Now, the work in physics only has a meaning if you apply a force and if the object moves. There is motion, right? So if I can sit here and push on this board all I want, I might get tired, but in physics, I'm not doing any work because, yeah, there is a force applied, but there is no motion that comes with it. There is no displacement. Okay, that's the idea of work in physics. Now, if we look at this picture here, we move into the right on the board. So you can see clearly that this normal force and this mg have no business in moving the object. So they basically don't do any work. And the other thing I want you to pay attention to is that if you look at the angle between the direction of travel and the normal force and the mg, that's perpendicular. The direction is a 90-degree angle. And that's going to come in later when we talk about how we find the work numerically, how we calculate it. Now, this Fa is definitely contributing to the displacement of this object. Okay, and the angle between this Fa and the direction of travel is 0 degrees. This force, F, is also contributing to the displacement of the object, but in a bad way, kind of, in a negative way. In other words, it's not allowing you to move to the right, but it's trying to hold you back. So the angle between Fa and the direction of travel is 0. Now, in this case, we say, well, that Fa does positive work. The force of friction is acting opposite the direction of motion. Now, we say that this force does negative work. And keep in mind that the angle between the direction of travel and the force of friction is 180 degrees. So somehow, we have to, the formula for work has to have the angle in it, okay? So it covers all the cases, okay? Now let's look at a different scenario where I take the same object, but this time I pull at a certain angle. Let's just say that angle is theta. Well, my forces are still the same, except the Fn is smaller because I'm pulling up. And so basically the Fn plus the y component of this Fa, or the vertical component, add up to mg. I mean, this is not drawn to scale, but I can extend this. And here's your friction. And again, you're going to displace the object to here. Now, is there more work or less work done after I put the force at an angle? I'm going to call these cases 1 and 2. Well, let's think about it. This force here, not all of it contributes to moving the object at distance d. It looks like only the horizontal component of it is what's moving you forward. The vertical component does not move you forward at all. Okay? So in this case here, I think the work in part 2 is definitely less than the work in part 1. I'm doing less work. Okay. Now, I think we have to write a definition for work, or a formula for work. So work is basically a force times the amount of displacement, okay, times, I have to bring in the angle. Now, if you look at this picture here, only this horizontal component does the work. Well, this horizontal component is just FA times the cosine of this angle. So I have to introduce a cosine of the angle. Now, that angle is the angle between the force and the direction of the displacement, okay? So that's where the angle is. Okay, so let's go back to previous case. Well, the normal force and the mg, we say they didn't do any work. And I think the formula will confirm that, because now you're dealing with an angle of 90 degrees between the normal force and the direction of travel, or the mg and the direction of travel. So that makes sense. And we say that the force of friction contributed in a negative way. So it basically did some negative work trying to slow you down, or to give you less of a displacement. So the cosine of 180, you should know from your trig class that it's -1. So that's how you end up with the negative work. Now, the beauty about working with the work and energy is that we don't have to deal with vectors anymore, right? When we dealt with forces, we had to deal with vectors, breaking down the forces and stuff like that. You're going to see that in this unit. Everything we're going to work with, or pretty much almost everything, is going to be scalar, which makes things a lot easier to deal with than to deal with vectors, right? So a lot of this stuff that you're going to see in this unit could have been done with Newton's laws, could have been done with kinematics, right? But I'm going to take a different approach. Everything is scalar, so the math should not be that hard to do, right? Conceptually, it might be challenging here and there, but the math should not be that bad. Okay. Another thing, I do not want you to confuse force and work, right? Force is just how much push or pull you do in an object. Well, with work, you have to push or pull, and it's got to be some kind of displacement, right? So there's a big difference between the two, so don't confuse them. Now, here we're talking about the work, for these two scenarios here, I'm talking about the work done by a constant forces, right? Force of friction is constant. The applied force here is constant. Now, let's see what happens when we're dealing with the work done by some force that changes with displacement, right? So as the displacement increases, the force is no longer constant. And the example I'm going to use for that is a spring. So, and I'll let you play with this in class. It's like if you take a spring and you want to stretch it just a little bit, you're going to actually feel that the spring has a little bit of a tendency to want to go back to where it started from. See, this spring doesn't want to be stretched. So if you pull on it, it will pull back, right? Now, if I want to stretch it more, I feel that it's getting harder, right? If I pull even more within the limitations of the spring, if I pull it too hard, right, it will just get to a point where it cannot come back, okay? So if I stretch more, I feel like there is a bigger force trying to bring it back. So in this case here, the force is no longer constant. And we'll do a lab on this, and you're going to see that the force is actually directly proportional to the amount of stretch that I call x. So if the spring was like this in the beginning, and I stretch it, and it gets to here, this is the x. Okay? So I'm stretching it to the right, but the spring is trying to go back. So technically, in terms of vectors, okay, as a scalar, it's just f equals kx. In terms of vectors, this f is basically always opposite to the direction of stretch or compression. See, if I compress it, it wants to push back and get back to where it started from. If I stretch it, it also wants to do the same thing. But for us, in this unit, we're just going to say f equals kx. We're going to do a lab to prove that. We're going to use a bunch of springs and graph some data and see if that's really true. In other words, we're going to take a spring, hang different masses. We'll get to that when we get to that. Well, in cases like this, I cannot use this formula, work equals F times D, which is basically the displacement cosine of theta. Well, the cosine here is just It's just 0 degrees, right? If I'm pulling to the right and I'm displacing the object to the right, the angle is 0. I can't do this, okay? So you're going to see that the work done is not kx squared. And the reason for this is this force is not constant. So keep that in mind. So this is a no-no. Now, I'll show you quickly what the work done on the spring will be. Now, if I graph this equation here, which is F in terms of as a function of the displacement, it's pretty linear, right? And this number here, or this letter K, is what we call the spring constant. So it basically tells you, well, how much force you need to stretch the spring a certain amount. Now, let's say the force to stretch it this amount x, okay? I'm going to write this as force. This is displacement from equilibrium, okay? And this is the curve, the line. So if I call this force F, if I want to do the work equals FD cosine theta, I have to kind of like, I start with like very little force, I end up with a lot of force. So I take the average. If I take the average of this between 0 and F, which is half of F, then I can use the W equals FD cosine theta. So then the work will be F, which is basically half of F, that's the average, times X. That should give me 1/2 kx squared. So in other words, to stretch this spring by an amount X, right, you have to do this much work. And by doing that much work, you store in that much energy in the spring. So just be careful when you finding work. Now, for any force that's variable, okay, in order to find the work done to stretch at a certain amount, all you have to do is find this area, okay? Now, if I find this area here, and you can do this in calculus, but I think I showed you just a quicker way of doing it. To find this area, it's just going to be the area of a triangle. So it's 1/2 base times height. And this F is K times X. Okay. So let's do an example here, or two examples. First one, John, can you lock the door from outside? Thanks. Okay. So I have a force here, let's say 300 newtons. I have an angle of 60 degrees. I have a mass of, I don't know, maybe 10 kilograms. I have a normal force. I have my mg. And let's just say there is friction. And I'm going to say the coefficient of friction is 0.1. Okay. See, N and mg don't do any work. Okay. And I'm going to displace this object maybe at a distance of 2 meters. So the work done by the applied force, so I have to be specific, is equal to the applied force times, and you will write the formula, of course, times the displacement cosine of 60. And you can figure out the answer, and this should be positive. Okay. The work done by the normal and the mg, those are 0. The work done by friction is equal to the force of friction times the 2 meters and cosine of 180. Okay. Now the force of friction is equal to mu times Fn. And the mu is 0.1. And the Fn, you can see here that we can calculate that. So N plus 300 sine of 60 is equal to mg, which is 100. So you can figure out your N, right? And you can put it in there, and then you can just figure out what the work done by friction is. So work is specific to certain forces. Okay. Now let's do an example that you have to know for the lab. So if I'm going up the stairs to the second floor, right? If I'm going up the stairs to the second floor, okay? Now, each time I go in this direction, right? I'm working against gravity. Each time I go in this direction, I'm not doing any work. I'm only doing work when I'm going in this direction. Okay? I'm not doing work in this direction. I'm definitely doing work in this direction. So when you're doing work, the only thing that is going to be the force you're working against gravity times the cosine of 0 degrees, basically, times the sum of this distances here, which, if you think about it, from the first floor to the second floor is just, if you add up all these heights of the stairs, you're going to get the distance from the first floor to the second floor. And you're going to do a lab on this. Now, we're going to talk about power. Okay? Now, see, I can do work. I can apply a little force and go from this point to this point. I go 2 meters, right? And I can also apply a bigger force and still cover 2 meters, right? So if I have 2 machines doing this, or 2 people, and I want to figure out which one is more powerful, I have to figure out which machine or which person does this the quickest. So now that's where the concept of power comes in. So power is basically how fast we do the work. It's the rate at which we do the work. So power is work divided by time. Now, I forgot to talk about the units for work. The work is in the units for work is joules, which is technically newtons times meters. If you look at the formula, because it's FD cosine theta. This is in newtons. This is in meters. The cosine of theta is unitless, right? So a joule is unit times meter. So I'll just give you an idea of what 1 joule is. 1 joule is an extremely small amount of work. And that's basically, think of it this way. It's just like taking a quarter-pound hamburger, just a small example, and raising it about 1 meter above your head. So you know what a 1 meter is. So you're just taking a quarter-pound hamburger and just raising it up to there. Okay, which I don't think takes a lot of work to do. So joules, and the time is in seconds. Now, joules per second is what we call watts. So power is measured in watts or kilowatts or horsepower. Now, 1 horsepower is basically 746 watts, or maybe sometimes we'll say that it's 750 watts. Now, another unit we can do for energy is power is work. Now, when you do work, it basically becomes energy stored in whatever you're doing work on. Okay? So which means energy is power times time. Okay? So a lot of times we express energy in terms of power times time. And the electric company, companies will do that. So power can be expressed in kilowatts times hour. So kilowatt hour is not a unit for power, but it's a unit for energy. Okay? And I'm going to do an example here. So let's just say I'm going to try to the question is I'm going to try to find the cost to run this projector in the classroom, okay, for a whole year. Now, I'm assuming that I run it for about, let's say, 4 periods, 4 hours a day, a little bit more than that, but that's just about, let's just say that. Okay. Now, the wattage for the projector, I looked it up earlier, is about 250 watts. Okay. Now, to find the energy consumption, you take your wattage in kilowatts, so that's 0.25, right? And you multiply by how many hours you run it. So in 1 day, now we have 180 days of school. So in 1 day, I run it for 4 hours, okay? Times 180, well, just 180 days of school, about 185 or something like that. That's going to give me how many kilowatt hours. So I can do this in here. So So 0.25 times 4 is 1. So it's basically 180. So it's 180 kilowatt hours a year. Now let's say the cost of electricity, I'm just guessing, let's say 3 cents per kilowatt hour, not per hour, kilowatt hour. Well, how much money does it cost to run this projector for a whole year? So basically just do 180 times 3, and you should get about 540 cents, which is about $5, $5.50. Okay. Now I'm going to do an example here that's a little bit more complicated, trying to figure out the work done by different forces when we're going up a ramp. Okay. So I have an object that I'm going to take from down here to up here. Okay. And this object is going to start from rest. Let's just say it has a mass of 2 kilograms. And it's going to cover a distance of 20, let's say 30 meters in 20 seconds. Okay. And let's just put in, let's make this angle 30 degrees, and let's just put in some friction there, right? 0.1 kinetic friction. Okay. So I'm going to take this object, I'm going to redraw it here, and I'm going to make a list of all the forces acting on it. So I'm going to do a free body diagram. So I have definitely my mg. I have my normal force. And I'm going up the ramp, so there's got to be some friction going the other way. And I'm applying some force here, so I'm going to call it the applied force. All right. So I'm going to do the work done by the applied force. Now this is going to be the applied force times the d, which is 30 meters, and I'm traveling up the ramp. The force is up the ramp, so there is an angle of 0 degrees between them, so cosine of 0 is 1. The trick is to find the applied force. So now you have to go back to the forces and find to Newton's second law and find the Fa. So I can see that I can break this down into components. So I think it should say Fa minus Ff minus mg sine theta equals ma. Okay? Now, I think you can find Ff, which is mu mg cosine theta. You can find this. The acceleration, I think you have to rely on the information that's given here to get the acceleration. And after that, you can find the Fa. I'm not going to do it, but I'm going to just give you a hint how to do it. So the initial speed is 0. I don't know the final speed. I know the distance traveled, and I know the time. So I don't have the final velocity. So you have to figure out which equation to use to get the acceleration. Once you get that, you can figure out the Fa. Now you have the work done by the applied force. Later on, when we do energy, I'll show you how you can do it without going back to the forces on an inclined plane. Now, the work done by friction is basically the force of friction times the displacement cosine of 180 degrees. Because friction is down the ramp and you're moving up the ramp. So there's 180 degrees between the two. Now, the force of friction is basically the mu times the Fn, which is mu mg cosine of 30. The work done by gravity, okay, is basically the force of gravity. Well, you know what it is? If I break the force of gravity, if I break the force of gravity into two components, this component down here does not do any work. Only this one does the work. So I can say, well, you know what? Only mg sine theta does work. And the distance is still d. Cosine, well, between this direction of travel, this direction of the force and the direction of travel, there is 180 degrees. That's not always the case. Just imagine if this thing was sliding down the ramp, that angle would be 0 degrees. Okay. Now here's a quick shortcut. This d sine theta, if you look at it, it's d times sine theta is basically just this height. So if you can figure out this height, then you're good. Okay? And you can be either a plus or a minus depending on whether you're going in the direction, the mg sine theta is in the direction of travel or against it. So now we can figure out the work done by gravity, which is technically mgh, either positive or negative, depending on the scenario. Now, the last thing I want to do is, well, not the last thing. The work done by the normal force is just zero, because no matter what you do, you're always going to be perpendicular to the direction of travel. Then if I want to find the net work done on this block, all you have to do is add up all these three. So the sum of the works. All right? And that's work for you and power. Now, one quick thing about power I forgot to talk about is power is work divided by time, which is work is F d over t. Well, this d over t is the average speed. So this can also be written as F average velocity, or average speed actually, because it's power is a scalar quantity. Everything we work and power are both scalar quantities. And I think that's it.
All right, I'm out. Peace.